Department of Atmospheric Sciences, and yes, it's there. And also Paris École Normale Supérieure, I think. I got to know Michael in the beginning of the 1980s. Then I think he was in New York, Courant Institute of Mathematics, professor, and had several PhD students that also have influenced data assimilation, Dick Dee and Stephen Cohen in particular. And I think then after New York, he moved to UCLA, where he was head of the Department of Atmospheric Sciences, something like that, and where his interest mainly turned to climate studies, I believe. For me, he's, I think he's two things. He introduced the idea of common filtering into atmospheric sciences for data assimilation, and that helped us to understand what we are doing. Before, maybe we were a bit confused what we really were doing. And also, I would say that his provocative, constructive attitude during seminars and other social events, it has also been a very good for the progress and collaboration. So please, Michael.
Okay, it's a great pleasure to be here. I mean, I have known about Nordita for a long time. As some of you already know, I spent 3 months at Stockholm University in the late spring and early summer 1978. But actually, I'm visiting Nordita for the first time. It's a pleasure to be back in Sweden. It's also a pleasure to, stumble upon Niels again. And indeed, yeah, we met at this, the first data assimilation seminar, as they call it, which is really a summer school at the European Center for Medium Range Weather Forecast, which was in, I think, spring of 1980, something around that time. So I understand that you've had quite a few lectures on data assimilation, and the main thing that I want to get to is really parameter estimation and applications to new areas, but I will go through some of the stuff that got us here. And actually I have a reserved transparency which comes out of that either the book that was co-edited by Leonard Bengtsson, Erland Schavian, and myself. Leonard Bengtsson, who is Director of Research at the European Center at the time, and Erland, who is that now, and myself. A book which came out in the Springer series on applied mathematical sciences, but have a lot of transparency, so I'm not sure that I will actually get to that. So again, although my attention has turned to a number of other things in the meantime, I've sort of been, as in other areas, a lucky dog in terms of lots of young and very good people sharing my interests. And these are some of the more recent collaborators. These are the logos of the two institutions that I'm now associated with, École Normale Supérieure and still UCLA. These are some people, I mean, Dmitry Kondrashov is going to be mentioned in two contexts later. Yuri Spritz mostly in terms of applications to space physics. Alberto Carassi and Anna Trevisan in connection with a sort of nonlinear dynamical systems point of view on sequential estimation. And these people I won't have the time to really mention their work, but we've been working on applying these ideas of parameter estimation to macroeconomic models. Okay? So, if you really know everything that I'm going to tell you on some of these slides, please just urge me on. Again, from my years at the Courant Institute, I had a lot of very distinguished colleagues over there, and one of them was Joe Keller, who said that you have to start any general talk very slowly, so at least for the first 20 minutes everybody is with you, and then accelerate to the point where you've lost everything. So, okay. So, urge me on if the part that you all understand is already there. So, I'll start with some data and then with some basic ideas, which I really, it was very interesting to listen to Niels's talk yesterday, because indeed, now, when I became interested in this, actually during my student days at the Courant Institute, things were pretty primitive. I mean, your table of methods from the late 70s sort of indicates there were things like piecewise polynomial interpolation and so-called optimal interpolation, which was some sort of linear, local linear regression and so on. And you know, in the meantime, things are very evolved, and everybody's talking about various forms of the Kalman filter, and 3 and 4 and 5 dvar and so on. And and of course, this contributes in an important way to the quality of numerical weather forecast, but the improvements are somewhat marginal. If you look at you know, Niels's transparencies from yesterday, you know, there's about this. If you did a lot of work, you gained another few hours of forecast accuracy and so on. So, you know, my attention has been turning to other areas of application mostly. Anyhow, I still think that these basic ideas are important, and then I'm going to get to parameter estimation. I'm obviously not going to cover all of this, but I will talk about parameter estimation. I'm actually going to skip this part on subgrid scale parameterization, which is very important. And out of the novel areas of application, I will only cover space physics. Okay? So, main issues. You know, the solid Earth stays put to be observed on the timescales of interest, except big earthquakes. But the atmosphere, the oceans, and many other things do not. Okay? So they evolve while they're observing them. So there are two types of information: direct, the observations, and indirect, the dynamics, which in some sense convey information the way that we distill all we know about past observations of the system. And this is a point that, you know, Tony Hollingsworth, RIP, liked to make a lot. And both these types of information have errors. Okay? We're not in paradise. We don't have perfect knowledge, you know, on anything, not even on the dynamics. And so we want to combine the two kinds of information in an optimal way, or several optimal. You know, optimality is really defined rigorously in a certain context, but non-rigorously is better than other stuff. So what I call advanced data simulation methods provide such ways. So one is essentially sequential estimation, the emphasis being that, you know, you update as you go along. And this is the Kalman filters, various versions, you know, extended, ensemble, unscented, whatnot. And the other one is basically the control theoretical point of view, the adjunct method of methods. And so the two types of methods are essentially equivalent for simple linear systems, finite dimensional linear systems. That's the so-called duality principle. But their performance differs for large nonlinear systems in terms of accuracy and computational efficiency. And that's where the trade-off occurs. Okay? So, you know, you're talking about combining them. As you see, this is not a transparency that I made yesterday after your talk. I did, you know, study optimal combinations as well as improvements over kinds of operational methods. So, you know, there are some places that still use optimal, so-called optimal interpolation for dvar. PZAS, which is what they've been using, physical space assimilation system that they've been using at Goddard, you know, some of my students are, and, you know, ensemble Kalman filter, etc. So, okay, data. So this is out of this book that I was alluding to. It's in the preface, and this was the observational system that we had. So the seminar was actually in 1980. The book came out in 1981. It was a selected set of lectures from the seminar. And this is the set, the observations that we had. So this was on someday in January 1971. And for those of you who are too young to know, FIGI is a so-called second-order acronym. You know, it was, there was something called the Global Atmospheric Research Program, GARP, and FIGI was the first GARP global experiment. But then when there wasn't a second one, it was renamed the GWE, the Global Weather Experiment, and actually, you know, the number of observations has not necessarily been going up a lot since then, but this just shows you the great variety of observations that you have, you know, from drifting buoys, which only give you surface pressures, to cloud drift winds, so this is over one 12-hour interval, okay? Aircraft, again, velocity vector, so you see, you see where the planes go, and then you have ship and land surface, so surface pressure, surface temperature, surface velocities, and these are the various numbers of these observations. And then really, the whole interest in data assimilation, people obviously have been doing some form of data assimilation since the beginnings of numerical weather prediction. Okay, so basically, the first theoretical attempts, there was the one of Richardson that Niels mentioned yesterday during World War I. But then basically during World War II, people realized the importance of this, and there was a so-called joint numerical weather prediction unit in the United States, which developed in first of all, the John von Neumann effort at Princeton, and then the operational effort of the joint numerical weather prediction unit. So people, you need observations to compute the weather, and it was already realized by ghil and Bjerknes at the beginning of the 20th century that numerical weather prediction is or should be an initial value problem for a set of partial differential equations that govern the atmosphere. But the problem was at all times and still today that you never have the initial state. Okay, so it's a wonderful initial value problem if you have the initial state, but you don't. So you have to make up for that in some way. So people had been doing various things, but it's really only the advent of satellites that make people realize the fact that you have this very different problem with data streaming in as your solution evolves. And when you only had the so-called conventional network, before there was a World Wide Web, there was another WWW, the World Weather Watch, okay? And so while people were only using conventional network, they had agreed to have so-called synoptic observations, that everybody would take observations at the same time, so as to ideally have an initial state. But still, that state is very incomplete, because originally it could only be done over the land masses, where you had evolved societies that could afford weather observations and so on. But then when the satellites came along, that really gave the impetus to seeing data simulation the way we see it today. So these polar orbiting satellites, that spin the Earth, were very important. And then you had, okay, so the cloud drift winds are from geostationary satellites, so okay. Then you have balloons, radiosondes, so this is mostly the conventional stuff. And the total number of these observations is of the order of 100,000 scalars per 12 to 24-hour interval. Now, why is that important? Because basically that is the characteristic time of evolution. We talked yesterday a little bit about Rossby waves and inertial gravity waves. That's a characteristic time of motion of weather systems. If you look now on your television on good weather forecast, you see these things, the clouds that evolve, and they evolve on this characteristic time. So the interesting thing is that you have about 100 observations per significant degree of freedom, in other words, per something that characterizes this large-scale situation, per significant time interval. It's an enormous amount of data. And it's truly puzzling and frustrating why we're doing such a lousy job of weather forecasting. Sorry, Niels. Okay. You know that. I mean, you know that better than other people. And, other people in the room only have a problem, well, when do you take your umbrella or not? But Niels and people like him, I mean, it's really frustrating to do all this work. And then, like yesterday morning, it was raining when it was supposed to be good weather, right? Okay, so, the reason that you have this is because it's a tough problem. Okay. Now, he also mentioned quality control. This is actually out of, I think, Roger Daly's book on data assimilation. This is now January 1984. So again, you see that these are 1516 observations by clear sky observations. This is quality, QC's quality control. So this is, you throw out the stuff because something from beforehand, you know, again, Tony Hollingsworth used to be very proud. He gave some talks in which he said, you know, he got this weather observer on, I forget which island in the Indian Ocean, with his pants down on a given day. Clearly he was drunk or had forgotten to report on. You know, you can actually tell from the large-scale picture if an observation is doing something funny. On the other hand, of course, it is also a problem because it is well known that the British Antarctic Survey, you know, used to, NMC used to throw out a lot of ozone observations over the Antarctica because it didn't make sense. Okay, and then it was this guy from the British Antarctic Survey who made some local observations and said, oh, they do make sense. And that's how we discovered the ozone hole, which used to be thrown out. Okay, so quality control is a dangerous endeavor, as it was pointed out yesterday. Okay, so ocean data now. In the past, so, you know, that's actually the way that I became interested in physical oceanography, because I was pulled by the sleeve. You know, when these people started getting data, they realized they had to do data simulation. So, you know, this is the total number. These are so-called mechanical battery thermographs. This is the equivalent of radiosondes in the ocean. So, and this is so-called expendable battery thermographs. So the total number of these used to be 10 to the minus 4 less per degree of freedom per significant time interval. And now, with satellite oceanography, it is still about 10 times less than for the atmosphere, because basically you have only surface data. You have very few data. So, you know, the surface data come from satellite oceanography. All these trajectories, I like this transparency because I got from Tony Lee at JPL, you know, it shows you again how these satellites spin the Earth. Okay, and then you start spilling over into new areas. So, you know, space physics is now coming to the point of having multiple observing platforms. Again, you have ground-based observations, and then you have multiple spacecraft. You know, it used to be, again, it's a situation a little bit like the one that I witnessed in oceanography at some time. And, you know, it used to be that people went out to sea and threw a bottle overboard and hauled it back in, and they had a few of those, and then they went back to port on their own 5 papers. Okay? And now they have a lot of data, so, you know, maybe they don't even go to sea out anymore. So likewise, you know, you prepare the whole lifetime for one instrument on one satellite, and then you wrote all the papers out of that. Well, now it's been changing. So again, let me see whether I can show you a little movie, which again I think is incredibly interesting and tells you a lot about data simulation, which I have from Bill LaHoz at DARC, at the Data Simulation Research Center at Reading. Okay, so these are ozone data. You know, it has to do with this. So these are the satellite trajectories, and this shows you the level, you know, the ozone concentration in the stratosphere from this instrument on top of these satellites. This is the ozone hole. So, you know, this is the actual observations. This is the assimilated field. Okay? So, let's play it. Okay, so you see these satellites that circle around, and the assimilated stuff, which is moving slowly. Okay? So this is how you get, you know, out of a few observations. Okay, so the single hole splits up into a dipole, and all sorts of other interesting things happen when you combine the evolution equations with these very partial data.
What are the gaps? Because you have hairy in the narrow and then you have gaps.
Oh, you know, there are all sorts of things that get in the way. Frankly, I don't know for ozone, but for the troposphere, it's clouds.
Yeah.
Okay? So, fine. So, okay. Okay. So, fine. So now we're done with the data. So let's talk about the basic ideas, data types and issues, how to combine data with models. So they're basically, the whole idea is that you have transfer of information either between variables that you do observe and those you don't, or between regions that are data rich, like the land masses of the northern hemisphere, and regions which are data poor, like the oceans in the northern hemisphere, and basically all of the southern hemisphere. Okay? So again, you've seen this, but again, I will try to make the connection between this and sequential estimation. Okay? So simple illustration, you want to estimate the temperature of this room based on 2 readings of 2 thermometers by a linear estimate. Why linear? Because it's easiest. Okay? So the interpretation in the context of sequential estimation will be that one thermometer is the so-called first guess of the numerical forecast model. In other words, information carried forward from the past. And T2 is the actual observation. Okay, radio, sound, satellite, whatever. And this estimate is the objective analysis. And again, it's called objective. I don't know whether you were told this, because before, using computers, people just looked at maps and there was a subjective analysis, from all the observations you tried to make up a field. Okay, so assumptions, T1 and T2 are unbiased, and all of these assumptions are wrong. Okay, the instruments aren't unbiased. For instance, the radiometers are biased towards warm temperatures. The forecast, the first guess is certainly not unbiased, but this is, all of you know the story about the lamppost? Okay? Okay. Yeah? You do? No. Well, there's this man who comes home back home late at night, and his neighbor is on his knees, fumbling around. He asks him, "What's the matter?" "I lost my keys." So our guy also gets down on his knees, fumbles for a while, and doesn't find them. So, "Where did you lose them?" "And over there." "So why are you looking here?" "Well, this is where the lamppost is." Okay? So this is the lamppost. The assumptions are the lamppost. Okay. So they are unbiased, so we would like the estimate to be unbiased. And then basically it says that we're going to make a convex linear combination of these observations. So alpha 1 and alpha 2 are the coefficients are positive, and they sum to 1. So I can also write it in this way. Okay, so instead of writing it as I did before, alpha 1 T1 plus alpha 2 T2, because 1 is the first guess from the okay, I'm going to write it in this way. And then if the 2 are uncorrelated and have known standard deviations, this is a little trick that I learned from Chuck Leaf. You call the inverse of the variance the accuracy of a measurement. Okay, so you have accuracy 1, accuracy 2. And so the minimum variance estimator, also called BLUE for best linear unbiased estimator, is given by T1, your first guess, plus this ratio, the accuracy of the observations divided by the accuracy of the first guess and of the observations, multiplying the difference between the observations minus the first guess. And this is called in engineering literature the innovation vector. In general, it's a vector. And in meteorology, often the so-called observational residual. The difference between the actual observation and what you thought your observation ought to be if you knew nothing else. And the accuracy of this BLUE estimate is the sum of the accuracies of the 2 ingredients. Okay? Which is larger than the better one of the 2 accuracies. Everything in principle if the assumptions hold. Okay? So now, what about, so, to me, the Kalman filter looked like the natural thing. You see, people were essentially doing this, okay? Except that they were using these linear regressions, which they used to call optimal interpolation or whatever, and they just kept doing it, in a so-called forecast assimilation cycle. You got observations at synoptic times first, you update it, and then you proceeded like that. So that was sort of the natural thing to do. Now, what is the theoretical framework? Well, the common filter was just a linear thing for a linear system and actually finite dimensional originally. So the true evolution is deterministic plus stochastic. The true state vector time ti plus 1 is, this is the model, which is nonlinear. Essentially the nonlinear evolution operator associated with the PDEs, you know, the resolvent or whatever you want to call it, x true at time ti, plus some stuff that again you assume random and which you assume to have mean 0, etc. And to have in the first known covariance matrix. Okay? Now this true evolution generates two things. One, it generates the observations. So again, this can be a nonlinear observation operator, again with some noise. And again, the noise here is not so much the instrumental noise as the sampling noise. Okay? And again, you assume you know this, which is absolutely untrue. And then this is your innovation vector, again, the yi super 0 for observation, O for observation minus this operating on the forecast. Okay, and then it also generates the prediction, which until very recently, so this is what happens in nature, this is what happens in your computer. Okay, and until very recently, this was deterministic. In the meantime, people do have stochastic parametrizations. Luckily, you'd have to change this. So you have xf at time is operating on the analysis at time I minus 1. And you have, so what the characteristic thing that did not used to be done before, only in a very primitive manner, is that you also are trying to advance the covariances. And this is what's computationally expensive, and this is why all these experts, you know, Niels and Leonard Benson and Roger Daly and Tony Hollingforth, laughed me off the podium in 1980. Because they said, you are never going to be able to compute this. Okay, and there's a rule in science, never say never. Okay, so people are doing it now. But this is, how to approximate this equation is really the, you know, the major difficulty of this sequential estimation approach. And then so you are combining the observations with this. Yeah, and there is a conceptual difficulty because, you know, many people think that plus noise should be here. That the proper framework is that the plus noise is there. Okay? This is what you know, that happens in your computer. This is what nature does that you don't know. Okay, so now you combine these two things into an update which is probabilistic, and that ratio of accuracy 2 divided by accuracy 1 plus accuracy 2 is a so-called gain matrix, and the symbol K obviously stands for Kalman. You know, he used K for Kalman. Okay? Okay, so this is innovation vector, etc. And another thing that's important is, so this is now the covariance matrix of the analysis, of the objective analysis, you know, the updated state. The identity minus this thing. So you expect it, in some sense, to be down. I mean, you know, it's not obvious because this is not a you know, necessarily a positive definite matrix, but in some sense you expect this to satisfy the thing that I told you, that the accuracy of your estimate is better than the accuracies of either observations or forecasts. Okay, so now transfer, so this is how to combine data with models, so now transfer of information between variables and regions. Okay, so this is sort of the example that I gave in 30 years ago, but I think it's still sort of cute to look at. It's a simple set of partial differential equations, linearized shallow-water equations in one dimension. So this is, you know, the dimension, and you have two oceans and two continents, but which are idealized to have equal width, and Tokyo is equal to New York by periodicity. Okay? So here's Hawaii in the middle of the ocean, this is San Francisco, New York, where I was at the time, St. Louis, London, and Tokyo equal to New York by periodicity. Okay? So this was based on the paper in that book, plus the PhD thesis of these two gentlemen. Okay, and let's see what happens. You do a little exercise, which you call a conventional network, so you only have observations over half the domain every 12 hours, which was a synoptic times. Now you sort of have them in 6 hours. And what I'm trying to illustrate here is the issue of the relative weight of observational versus model error. So this is a situation in which you are advecting observations from over the data rich, the continent, to the data poor, the oceans. Okay? And so you start out, so this is time in, this is 10 days. Okay, so you have observations twice per day. You start out with some large areas in the velocity vector u and v, and the phi, the geopotential. And so you knock it down when you have observations. This is over land, so you knock it down when you have observations, and it increases in between observations because you are feeding it noise. Okay, that's the noise in the evolution equations. Okay, and then you knock it down again, and you see that over land the thing enters a periodic cycle right away. What happens over the oceans, or again, root mean square error, you start out with the same large level of noise. You have a little bit of reduction of observation time just because you have spreading out of observations by multiplying with those matrices. Okay, there's some influence functions. But here it comes down much more slowly, but it still asymptotes to a periodic solution after a number of days. So basically remember that in the forecast simulation cycle, you are always in this region. Okay, I mean, you start a new forecast simulation system, you know, if you have a new model or a new data simulation method, but that transient is very fast, and you're always in this region. Okay, except that it's not exactly periodic because you don't have exactly the same observations every time. And now you look at the combined over the entire domain. Again, you knock it down over half the domain, and you enter this asymptotic region. Okay? And now, so let's look at this asymptotic covariance. It's equal to Q times R over, so you know, I did it in terms of the accuracies, but Q and R are the sigmas. Okay? QR over Q plus, so instead of having Q plus R, there's something here which comes from the stability. In the case of the Shalowater equations, they are neutrally stable, you know, they're hyperbolic, but because of the numerical method has to be stable, there's actually something that there's a little bit of damping. So if you had no system noise, okay, if you had no system noise, or engineers call it production noise or something like that, the asymptotic value of this would be equal to 0, okay? Q equals 0, we still have an R. Q were 0, you would have 0 error. In other words, what the Kalman filter achieves is essentially, remember that if you just have repeated observations of a random variable with mean, etc., the sigma of n observations is the sigma of one observation divided by square root n, which tends to 0, again, independent, identically distributed variables, IID, you know. You would essentially have an infinite accurate estimate of the temperature in this room. So what the Kalman filter does is it arrests the development. It arrests the evolution. There's no system noise. You would have an infinitely, you know, you would have 0 error as n increases, the number of observations increases. In other words, this transfer of observation or transfer of knowledge from data rich to data poor would be perfectly efficient. Okay? Now, what happens if your model error is not 0? Then it depends. If you have good observations, so R is much less than Q, then the P infinity is approximately equal to R. Okay? So this is what happens over land. Okay? If you have poor observations, I is much larger than Q, such that P infinity is equal to the system noise well divided by this thing. So this is what happens over here. So always, provided that this is less than 1, which clearly should be for a good numerical method, P infinity is smaller than the minimum of R and Q. Okay? So in other words, what I told you would hold for temperature measurements in this room holds for numerical weather prediction over the globe. Sort of. Okay? Okay, now this is just to show you that something like this actually does happen with real data and a real model. Okay, so this is actually after I had worked with this group at NASA for quite a while. I became interested in other things. So this is a paper that was published in BAMS in 1982. Milt Halen, Eugenia Kalnay, Raymond Baker, and Bob Atlas. And they're using, so basically they did an experiment in which, so this is conventional network, sorry, no satellite, and this is with a Figgy or GWE analysis. And it's geopotential at 300 millibars, so just a little bit under the tropopause. And this is, so we're looking at the 6-hour forecast, the first guess, minus the analysis using only conventional data or only figure analysis. You see that in this case, there are huge errors over land because you are blowing in lack of knowledge, it's sort of the converse, you are blowing in lack of knowledge over the western part of the American continent. Okay? When you have the figure analysis, which does have observations over the ocean, this discrepancy no longer arises, and you're having the conveyed information from the, from one agent to another. Okay. So, okay. Now I'm coming to something much more recent, so I'm jumping 25 or 30 years. Something about the stability. So I told you that in the linear case, it's clear that adding observations, will damp errors. What in a nonlinear case? So, well, first, let me just tell you what are the components of the error in the forecast analysis cycle. Okay, so this is the first guess error, the analysis error plus two components. This is a time step, or several time steps of 6 hours. This is the identical twin error growth, and this is a modeling error. So again, the psi in the previous transparency is essentially the exponent of A delta t, where A is a linearization of the modeling operator. So again, graphically what you look at here, this is the RMS error, so essentially the square root of the trace of the covariance matrix. Here is that for the analysis. This is the error of the climatology. This would be simple persistence. This would be a perfect model. This would be a model that is stable but has model noise. And this is the combination of the two, so this plus that, okay, in a very schematic, idealized sense. Okay? And it's very interesting because both Ed Lorenz and Chuck Leaf, whose name I already mentioned before, essentially did little exercises in which they tried to approximate these in scalar models. Okay, so there's some literature. Okay. So, now where I said, assimilation, observation, stability, consideration. So this is actually a paper by Alberto Carrassi, myself, Anna Trevisan, and Francesco Boldi in Chaos. Okay. So you have the free system dynamics, sequential discrete formulation. Okay. The forecast state is model integration from the previous analysis, corresponding perturbative or tangent linear equation, delta xf is equal to this. Now, if you look at the observationally forced system dynamics, again, the acronyms here stand for Bread Vector Data Assimilation System. If, so Bread Vectors, it's a thing that Eugenia Kalnay and Zoltan Todt and some other people at, and she started this when she was at NMC, then subsequently called LSIP, and continue after that. So if the observations are available and we're simulated, the evolution equation is the one that I showed you before in the linear case. This is just composition rather than simple multiplication. Okay, so you have the M acting on the previous analysis plus K, the gain matrix acting on the observation. So again, this is 1 minus KH. Again, there should be composition here times M delta XA times N. So the corresponding perturbative tangent linear equation, if the same observations are assimilated on the perturbed trajectories as in the control solution. This matrix, as I told you already, is expected in general to have a stabilizing effect. The free system instabilities which dominate the error growth during the forecast step can be reduced during the analysis step. So that's the key idea, but now in a, say, nonlinear setting. Okay? So basically we did two kinds of model, a simulation experiment with a low order chaotic model. So this is not the Lorentz 63, but a 40 variable version of the Lorentz 1996 model. So that's the chain of nonlinear oscillators, if you wish, around the circle of latitude, along the parallel. And there are various assimilation algorithms, pure replacement, direct insertion, which had been done by Anna Kreisbazan with a student of hers back in 2004. Replacement plus one adaptive observation located by multiple application, which Ed Lorentz had done with this 1996 paper. And replacement plus one adaptive observation, which is located now by this Brett vector data simulation system, and assimilated by assimilation in the unstable subspace. So that was the key observation. See, one of the ways that you can reduce the weight of that Riccati equation of the nonlinear, quadratic evolution equation for the covariance matrices is if you work in the unstable subspace. It turns out that in the atmosphere, as illustrated by a lot of work, there are really just a few unstable directions on the large scales. There's a lot of stuff in if you go down to cloud scale and so on. There was some discussion of that yesterday, but look at the large scale. There are few unstable directions and many stable ones. The many stable ones basically come from the fact that you can approximate a lot of what's going on by something like a nonlinear version of the Laplacian. Okay, so you have a lot of negative eigenvalues. Okay? So what happens here? So this was done in this previous paper. Okay, so this is the number of days. Okay, and this is the growth exponent. Here is 0. Okay, so this was simulation on the no observations. Again, you have modes which grow, and then as you improve your method, this is still above 0, but this and that are below 0. Okay. Now, what we did in this joint paper now, okay, is for the same model. This is now much cleaner results. This is the spectrum of the Lyapunov exponents. No assimilation, so, out of the 40 variables, there are about 12 directions which are unstable. And the various colors, all right, there's a free system, dark blue is just a simulation of the unstable space with 3-hour updates, 2-hour updates, and 1-hour updates. So you knock the exponents down further and further. Okay? So again, the idea is that if your free system might be unstable, why can you find out about it? Because essentially you control these instabilities by the assimilation, and if you do that deliberately in the unstable subspace, you are doing very well. And this is now with another model. So this is sort of an intermediate, in terms of hierarchy of models, which we use extensively in the atmospheric, oceanic, and climate sciences. There are toy models like Lorentz 63, 3 variables, and or even 40 variables, and then there are big GCMs, and in between there's some intermediate models which maybe would have been called GCMs 20 or 30 years ago. So this is a model due to Rick Rotuno and his associate Bell with NCAR. There are 64 points in longitude. This is a beta channel, 32 in latitude, and 5 levels in altitude. Okay, perfect model assumption, Q equals 0, assimilation algorithm 3D var, and then AUS according to this assimilation of the unstable subspace. And this is again now the spectrum of the Lyapunov exponents. Again, here is 0. Okay, this is the index. So again, out of this, so how many things are, this is 150, they're about 100, there are 10,000 variables or something like that. It's a respectable model. So these are just the first 100 of them. And you see that there are about 20 here in the free system which are unstable. And then as you improve, you bring it down. And so again, the leading exponent here is 1/3 of a day in the free system, doubling time 2.2 days. Number of positive exponents, oh, here it is, 24. Okay, Kaplan-York dimension, for those who know, is equal to 65. 3D var plus this bread vector data assimilation system leading exponent is much smaller. It's 2/1000 of a day. Kaplan-York dimension down from 65 to 1. And then, in this case, the leading exponent is already negative. Okay? So this works. Yeah?
I just have a question. In the time domain, how many the number of observations?
Well, it's just one. Remember, I think it's just a very small number of observations. I can't. I'm sorry. I don't remember now. But you can. I can give you the paper. It's just a small number of observations. I'm going to come back to this at the end. Okay.
Yeah, I just asked because the Lyapunov exponents are very sensitive to the size of the time series.
Oh well, sure. But these are, I mean. These are serious people who know them.
No, I know. So just to know if it's
I can't remember, but it's with a small number of data, with a really small number of data. So in other words, it says that in this nonlinear system, with 10,000 variables or something, the same simple concepts which I presented to you at the beginning do work. Okay. So okay, so. Okay, sorry, parameter estimation. I've been taking a lot of time over those simple things, but I think it's important. So let me. Okay, so there are essentially two kinds of approaches to parameter estimation. One is this dynamic approach, which I'm actually going to pursue here, which just says, okay, this is now in continuous time, some nonlinear model depending on the parameter plus noise observations, and you are not observing directly the parameters. You are only able to, so I showed you before how we transfer information from observed state variables to unobserved state variables, and from observed regions to unobserved regions. Here you don't observe directly the parameters, which is the typical situation. Okay? You can only observe the state. So the idea is a so-called augmented state vector, in which you say at first that your parameter does not change in time, but it could be periodic, it could be other things. Again, let's start with something simple. It's an augmented state vector that includes the parameter, so you're sort of reducing it to the previous situation. Again, I can't resist telling you again a story about mathematicians, ask a mathematician, you're giving a faucet and cooking range and the pot. How do you get boiling water? Well, you turn on the faucet, put the pot below, put it on the range, turn it on, let it boil. Now, what happens if you have already water in the pot? Well, you throw it out and you reduce it to the previous situation. Okay? Which sounds very funny, except that actually, in many cases, it's quite useful. Okay? So you reduce it to the previous situation. Okay? You stick the state parameter, the parameter into this augmented state vector. There are other approaches which deal with statistical models. I don't have the time since I'm already running late. Tell you about them, so let's concentrate on this one. Okay. So, example, one unknown parameter. Of course, there's more than one typically. There is augmented state, xk mu k. You have this, and you have some noise, and again, you're just observing the state. You're not observing the parameter. Again, you write down extended Kalman-Filter equations, so the parameters are not directly observable, but the cross covariances will drive parameter changes from innovations of the state. So you have, this is state-to-state, parameter-to-parameter, cross values, etc. So again, an important observation here is the parameter estimation is always a nonlinear problem, except if it's an additive parameter, which is not very interesting, even if the model is linear in terms of the model state. So you need to use something like the extended Kalman filter. Okay?
Michael, are you really going to allow your static parameter to evolve in time?
Yes, you're going to see that
Okay.
in the first illustration that I will give you. Okay. Everybody knows what the extended Kalman filter is? Basically, the state evolves fully nonlinearly. The Riccati equation is linearized. Okay. So here is a coupled ocean-atmosphere system. So it's again a so-called intermediate coupled model based on the work of Fifi Jin and David Nealon. And so again, there's a paper that by Dmitry Kondrashov, Chao-Jia's son, who's now with CSIRO, Dmitry still at UCLA, and myself in the monthly weather review. We actually started with a PhD thesis of Zheng Hao and was reported in, the first results were reported in a paper in the proceedings of the WMO Symposium on Data Simulation in Tokyo, and in my review paper in the special issue of the Journal of the Meteorological Society of Japan. Then the state estimation was done in this paper, but anyhow, this is the definitive reference. So you want to estimate the state vector, which is made up of temperature, sea surface temperature anomalies, thermocline depth, U and V, zonal and meridional currents, along with a coupling parameter mu between the atmosphere and the ocean, the so-called surface layer coefficient delta S, which determines the periodicity of the intrinsic modes in this ENSO model by assimilating data from a single meridional section. Okay? So these are so-called Hofmüller diagrams. We're in Sweden, so I'm really happy to refer to that, which oceanographers do this way, typically. So this is the tropical Pacific. It's one dimension in space, so it goes from from essentially New Guinea to South America, and this is time in years going in this direction. So this is a forecast using the wrong mu and delta S. This is the reference solution, which in this case is perfectly periodic, so you have positive and negative SST anomalies, and this is the result of the assimilation. Those were the preliminary results which were reported already in '95 in Tokyo. Now, this is out of this more recent paper. So basically, you're trying to compare the coupled model running free with the observations. So here is SST anomalies for a westward. So there are two kinds of regimes in this intermediate coupled model. One is so-called westward propagating one, and the other one is the delayed oscillator regime. So this is sort of westward propagating. So again, these are positive anomalies of SST. These are negative anomalies. They sort of have westward propagation. This is a standing strong oscillation in the eastern tropical Pacific. So for different parameter values, you get these different regimes. And what you see in the actual reanalysis is some sort of a mixture of these two. Okay? So now clearly this is not a very good model for what happens really in nature. Okay? So basically what we're going to look at is whether by figuring out parameter values, you can sort of reproduce what's going on in nature even with not so good a model. So this is what happens when you estimate the ocean-atmosphere coupling coefficient. So the heavy blue is the estimate. The dashed black is the true, so this is the correct mu value, which is constant. So this is, again, doing just idealized experiments. This is the error. So you start out with some value of mu, which is wrong, and you bring it essentially within the error bars. Okay? It doesn't tend to a constant value as you feed it partial observations of the states. Remember, there's just one. Remember, there's just one meridional cross-section. Okay, there's just one position at which you are observing the state. Okay? And this is what happens when you estimate the surface layer coefficient. Again, you start out with some wrong values. This is just anomaly, so this is 0 from the truth. Okay, so again, you bring it within the error box, essentially. So the error is just a standard deviation. Okay, now what happens when you use real data? Okay, this is now actually Central Pacific sea surface temperature anomalies. Okay, this is just the history from 1975 to 2005. These are two big ENSO events. Okay, historical, 1982-83 and 1997-98. Now, why do we say iterative? It turns out that you have to do two passes to go through this. Okay, but it converges after two passes. First iteration, second iteration, they only differ here in the beginning. You can't tell the difference past actually less than 10 years. And again, okay, so iterative mu estimate, iterative delta S estimate. So you see that these are no longer constant. Okay, remember we don't have the true value of these. These are just estimates of the standard deviation. So, okay. It turns out that if you tell it to change the parameter value, okay, you can actually capture these large events. Now, of course, this is in a hindcast mode, okay, after the fact, but I don't know how well this will work in a real situation. Okay?
So at the end of the, so for example, you have observation until 2005, and then if you want to produce.
And now I want to forecast.
Right.
Well,
so you take what value? You take the last one you have? Or
yeah,
take
you are trying to. Well, how you do that? How you do that? That's a whole new thing that I think we haven't really agreed with entirely with Axel what my next talk on Wednesday is, but I think I will be talking about one of these things that I omitted to talk about here, which is somewhere here I have empirical model reduction. Okay, so here, empirical model reduction. Okay, so that's actually what we do. You see, my group has been doing real-time ENSO forecasting since 1992. Okay, first by a method that we called SSA plus NEM, essentially doing what Sir Gilbert Walker, also known as Walker of Ewell-Walker processes, wanted to do, at the end of the 19th century, but pre-filtering information. So instead of just doing an autoregressive, which is terribly unstable and so on, we pre-filter the data with a single spectrum analysis that was doing pretty well. Now we're using some combination of empirical model reduction, and in the future we have a paper under review in the Proceedings of the National Academy of Sciences, the NAS, where I think we have even better ideas. Okay? But how you do forecasting, that's a whole new kettle of fish. Okay? But indeed, hindcasting, that's well known to people in the business, that the most marvelous results in hindcasting can collapse in the face of the real new situations. Okay, so I'm going to skip, obviously, this says, actual results in terms of these Hoffman diagrams. It's certainly not perfect because of model. Okay, so let me just say, because Axel, I think, is interested, we talked a little bit about sun climate. One of the novel areas, so we did some work on shock waves in solids, is actually done with a guy from Los Alamos. They're terribly interested how you can still keep what's called stockpile stewardship, okay? Without being allowed to actually carry out experiments, how you can figure out whether your nuclear arsenal is still as lethal as you like or not like, depending on who you are to be. So there's some experiments in solids that they like to do, and get some stuff on that, and they said we do some stuff on macroeconomics. Just run pretty quickly through the space physics application. So this again joint work with Dmitry Kondrashov, Yuri Fritz, and actually Richard Thorne, who is more, not so much on data simulation, more on the space physics side. So you have one particular satellite or instrument which is called CRESS. And don't ask me now what the acronym stands for, but we have observation starting in August 1990. So daily fluxes of relativistic electrons in Earth's outer radiation belt, 1 mega eV. So these are, so L, you can think of it roughly as being distance from the center of the Earth. Okay, it's not exactly that, but it's something like that. We have 2 Earth radii, 6 Earth radii, this is the outer radiation belt. And the black thing that runs through it is the so-called KP index of geomagnetic activity. Okay? And this is also joint work with some people at Los Alamos, who are the ones that launched satellites and so on. Okay, so you want to do parameter estimation. It turns out that you have a linear parabolic equation in this variable, in time t, and this variable L. And so again, you don't know the diffusion parameter, and you don't know this characteristic decay parameter. And these are terribly important for different things, including so-called magnetic storms or substorms. So what are the optimal lifetimes? Those that match the observation best. So if you just do this by trial and error, the way that the space physics people were used to do, it turns out that none of the pairs of parameter values tried fits the data well. You need to estimate the parameters really from the observations. Okay? And so here is essentially, again, you converge to some real values. So actual errors for state estimation, actual errors for state and parameter estimation, and then blue EKF estimated error, in other words, a trace of the covariance matrix. And basically, you know, this is again a trick that engineers know well, that you can play with the assumed uncertainty in what you're trying to estimate. And so when these are large enough, in other words, you assume in some sense that the model is not terribly good, you can drive the EKF estimates to the truths pretty rapidly. Okay? And, okay, let me skip this because I really want to get to the concluding remarks. We're already a few minutes. Okay, so, you know, computational advances since those times when, 30 years ago, when you had this data simulation seminar at the European Center, obviously a lot more computing power, larger and faster memory. Now, you know, the fact that no matter how much computer power you're going to have, there's always a question about what you're going to do with it. There was some discussion yesterday about that. You know, do you run an ensemble of low resolution or just one forecast? So, you know, software, again, there are better numerical implementations of algorithms, automatic adjoints, various kinds of sparse matrix algorithms in order to approximate the Riccati equation. Then ensemble filters where you don't have loss of orthogonality and so on, efficient realization. Then, again, the question here is, how much data assimilation versus forecast? So, you know, given the fact that these all contribute, you know, going back to this simplified diagram that I have at some point here, okay, that this and that and everything contributes to the forecast error, assuming that your only purpose in life is to have the best forecast, you know, for either for a fixed time or some accuracy for longer and longer times, you know, how do you apportion your computer power? And again, you know, the idea should be to design integrated observing forecast assimilation systems, and the kind of work that I showed you about stabilizing instabilities in the nonlinear context can contribute to rational discourse on this. Now, in terms of the number of observations, you know, in principle, you should need no more independent observations. And again, there was some discussion yesterday of super ops and stuff like that, you no longer, then degrees of freedom to be tracked. And, you know, you can use features like vortices, especially in the ocean where the vortices are small. You can look at the instabilities. You can look at trade-off between mass and velocity fields. So all of these basically tell you that you shouldn't need more observations than degrees of freedom. But, of course, reality, as I told you, is you have a lot more observations and you still are not doing very well. And still, the cost of advanced estimation is much less than that of instruments and platforms. So at best, you would hit it instead of instruments and platforms. That's a little bit, you know, overstating the point. But at worst, use inlet simulation to determine which instruments and platforms. So again, you know, much of this started from the observing system simulation experiments that were carried out in anticipation of FIGI GWE. And use any observations if forward modeling is possible. In other words, if you have an observing operator H that will map your state, and therefore your augmented state vector parameters to the observations. The satellite images, there's a lot of interest these days in directly assimilating. You know, people just used to do what was called, what's the word for when you try to provide information that is not quantitative information, it's visual. There's something, bogus data, yeah. People used to talk about bogus data, but you know, now people are actually trying to assimilate, you know, satellite data and so on for the observations, pattern recognitions and observations and the face-based statistics, etc. So theoretical concept can play a useful role in devising better practical algorithms and vice versa. It is an area that is very largely driven by what people want to do for improving numerical weather prediction. Judicious choice of observations and method can stabilize the forecast of simulation cycle. The trade-off between cost of observations and data assimilation. So then there was some question, well, can you even use, is it worth using ocean data for ENSO forecast, you know, given the fact that the ocean data is so lousy? And there was some sort of a conclusion at the workshop that I couldn't attend that it was not. It is. You do it right. They help estimate both ocean and coupling parameters. Changes estimated parameters can compensate for modeling imperfections. That was your question. Okay? So there's a lot of work on trying to put efforts together in terms of this research test bed. Here are some, I'm just going to leave you with some general references. Thank you very much. Again, apologies for running out of time.
Are there more questions to raise? Mike?
So obviously what sets statisticians apart from physicists or meteorologists is that statisticians do not like their static parameters to vary in time. Yep. They would rather explicitly incorporate a second stochastic process to describe the limitations of the model than, for example, more of a weak 4D bar type formulation. And I think that we have experience at trying to do it your way in quite general problems. And the usual finding is that the inference that you draw is very highly sensitive to the way in which you allow the parameters to vary in time. And that, given half a chance, the parameters, rather than the state vector, will adjust to rapid changes in the observations, which is not what you want, typically. It might be a useful diagnostic for when the model is breaking down, but it's not what you want for later assimilation. So I think it's intriguing that you're suggesting that we should allow our static parameters to vary in time, because that's not been the finding in stats at all.
Yeah. Well, you know, I'm a very reluctant statistician. I must confess to the fact that when I was an engineering student, I think in the second year or third year maybe, I tried to take a stats course, and I quit after the second or third session. Of course, at the time it was mostly cookbook kinds of approaches, you know, looking up the parameters of a t-test or something. And of course, the big breakthrough in modern statistics, like in modern, you know, PDs and so on, is computing. The fact that you can do non-parametric estimation and so on. So, without being trained as a statistician, I'm now supposed to be some sort of an expert in having developed things like single spectrum analysis and various other clustering methods and so on. I still, my heart lies with the dynamics, you know, I will admit. Of course, I greatly admire people who are real statisticians and are trying to also be useful. So I don't have, you know, I really don't know, because of course if you could, you see, thing is, ideally you should have an equation that for the parameters, which is not simply that they're constant in time. Okay? There's nothing that tells you that for a given model, you know, for a given model, you should have something like this. You should have some sort of an evolution equation.
Do you think so?
I think so.
But
Because, well, there's no model. You see, if you had a model that were perfect, and the difference between it and the true evolution of the system were really just a stochastic process, okay, then, of course, yes. But that's never the situation. It is not, okay? And actually what we are trying to do in this empirical model reduction is precisely to move away from the assumption of the difference being just white noise. Okay? It's some sort of a correlated noise, and it's multiplicative noise. You know, it's state-dependent noise.
Yeah, no, I agree with both of those points, and certainly what we're trying to do now is you know, using truncation type arguments, which Cecile Pendant knows very well.
That's right, I didn't get it.
Which Cecile Pendant, for example, knows very well. It's, you know, is to incorporate red noise as a diffusion process in the fast components of the differential equation. But you know, having done that, we would still like the parameters, the coefficients in the differential equation, to be static in time.
Well, you know, I think that again, to the extent that nature is not deterministic or stochastic, okay, and that we clearly have to take into account multiplicative noise, and you know, we're doing a lot of other work which is actually you know, rigorous on random dynamic of systems as well as numerical. I really don't know. I mean, I genuinely believe that there might be some use in separating, you know, I mean, ideally, again, you have some vectors, of course, so we denote it by M, the model, you know, some sort of a nonlinear model of X and parameters which are also vectors, okay, and then plus, and so here again you have some sort of a matrix which is also a function of X. And the extent to which, instead of having a representation like this, okay, and then now you also need to do something, to do something about the parameters, so there's no reason why, you know, this shouldn't have the same kind of form. Okay? Now, it might be, you know, ideally, well, again, ideally you would like to have some sort of a scale separation. You would like to call parameters things which are slow.
Yeah.
But you don't. Okay? I'm sorry, I mean, I think you had a talk here by Christian Franzke, who sort of represented the MTV point of view. You know, I'm sorry to say this in his absence, but I've said it in his presence. You know, I mean, this paper that I'm citing here in the volume edited by Tim Palmer and Paul Williams, you know, clearly shows that essentially MTV doesn't work. While our empirical model reduction does work. In other words, the models that we get, although they don't have the beautiful theoretical justification, actually do reproduce multimodal PDFs and spectral properties of the underlying system, which the results of MTV do not. And, you know, Andy Maida will tell you, oh, that's because we're not interested in that. Okay. But, so So ideally you would like to have something that you'd have some epsilon delta t there, but
that's a nice idea actually, to imagine that the parameters are on the scale separation slower than the slow components of your statement.
yeah. Well, if you can achieve that, then fine. But again, I don't have a lot of, so let's call n. I'm doing it. Let's now. I have no idea what this n is.
But you're going to have real trouble if your parameters don't have the scale separation, because they're going to confound with diffusion, and then you won't be able to nail them at all. Yeah? Unless you impose the scale separation, I think you have a serious identifiability problem.
Well, there is an approach which we're also trying to look at more closely now, which is this thing that's called more advanced formalism of including memory effects, okay, which Alex Chorin and some of his associates, Ula Haug, and I'm trying to forget, there's also a Greek guy, his name I forget for the moment, are trying to introduce into this data simulation problem specifically, okay? And in this approach, you do not assume explicitly scale separation. But again, there's always a problem of how do you get something computationally workable and so on. So I don't think that there is. We started discussing that, and I'm looking forward to go on. There is a really rigorous, there is some sort of a setting in which you get a rigorously correct solution of this problem. It's just a complex problem, and try to get the best approximation that you can.
Maybe we have.
Yeah.
I think it was some philosophical question. Do you use a knowledge about the physics of the process which you are going to predict in order to improve models, or you prefer forget all the physics?
No. Look, the thing is that in many engineering applications, you have relatively little, either little knowledge of industrial applications and chemical engineering and so on, and the common filter. People really try to pursue representations of the production process which were highly idealized. They didn't have, and they were trying to estimate as many parameters as they could. But it's not, again, the trade-off is not very efficient. I mean, you should use as much physics as you know in order to reduce the number of parameters that you need to determine. That's clear. But what the trade-off is between the degree of detail of your model versus the number of free parameters and so on, it's a practical problem. As Niels know, I mean, I really want to show this reserve transparency because, sorry, I forgot to show you this. It's lunchtime. Out of New York. May I go home? I can't listen. Out of New York. Okay, but I really wanted to show you. This was Dick Dee's thesis, which he published back in the IEEE Transactions on Automatic Control, which shows how to estimate noise parameters. Okay, so this is actually the one that, so this is after Gustafsson 1981. You might recognize something that you put in your contribution to that volume, okay? And this is reproduced in that review paper with Paolo Malanotte Rizzoli, that we published in 91 in Advancing. It's almost a book. It's 130 pages of review paper. So here is what the data simulation schemes and operation used were at the end of the 1970s. So I say successive correction, variation of blending techniques, multivariate 3D statistical interpolation, successive correction method, univariate 3D statistical interpolation, variational height, width adjustment. Really, so what I call here transition from early to mature phase of data simulation, numerical weather prediction, no column filter, no adjoint. All of this came later. Okay, and this is again cable out of this 1991 paper. The dual relationships between stochastic estimation and deterministic control, and which hold rigorously in the linear finite dimensional case. But this is what I call since I've seen data simulation evolve first in numerical way, then in metrology, then in oceanography, now in space physics. This is just usually I have to show this in successive stages. Pre-data simulation, few data, poor models, the theoretician. Science is truth, don't bother me with the facts. The observer, experimentalist, don't ruin my beautiful data with your lousy model. I've heard things like this, I swear to you, oceanographers. And when God, okay? Early the beta data, so models, stick the observations in, the insertion, nudging, advanced data simulation, plenty of data, fine models, extended ensemble conflict, 4D bar, etc. I call the second reality, and what I call the post-industrial DA, satellite images of the weather forecast, the climate movies, and there's also a review paper in which we discuss things like this. Anyhow, so, it's work in progress.
Okay, thank you. Maybe some more?
Lunchtime.
It's lunchtime, yes. Thank you again.
So I'm still here through Wednesday when I move to Uppsala, and I don't know whether
But you're talking here on Wednesday.
I will be here. I'm giving a talk in the morning.
On Wednesday, yes. And we have sometime perhaps on Monday afternoon as well.
Yeah. We have a discussion.
Let me remind you of the talk by Killing.
Yeah.
What? Yeah. Did I hear in the afternoon?
Not this afternoon.
No. Okay. So let me remind you of the talk by Killing in the Aula Magna. And so I can show you a Google map perhaps. There it is.
So, actually,
Yes.
yeah, it's perfectly okay to put this on the website if you want.
All right.
I'm reading it. Not the movie. I told Hans the movie is Villa House, and he allowed me to use it and to abundantly mention and
Yes.
thank him, but I don't know whether he wants it on the website. So maybe I will throw it out. Let me do that.
Yes, that's the. Oh, it's flickering, I don't know why. Anyway, that doesn't matter. So that's already the version. And so let me go to map first of all.
Okay.
It's really stupid, it's flickering. Maybe I should. And so here we have the place where we are right now. Shows us from here. So we are here. What I recommend, and that's the scenic way, is to go back to this road, over the bridge, and underneath, on the other side of the bridge, walk up this way to here. Here you see another bridge, but then you go towards this big road. And it's not a big road, but it's a fairly nice scenic walkway where there's a path on the left-hand side of this. And then you go all the way to here, and that's Stockholm University. And the Aula Magna is where it says Frescativägen on the other side, but you will see it from the inside. So Eric, go now closer to that. So first of all, a big engine, and one more. So that's how it looks like. I lost myself. Yeah, here we go. I lost myself completely here.
To the left.
What?
Left now.
Okay, that's all. So, one more. Is there anybody who would walk and so that's what I meant. You walk over here, over the bridge, to this side, and this way you walk up here, and until you come to this place, and then you walk to the right, over here, here's the walkway, all the way up to here, takes maybe 25 minutes. And now I should go to the satellite picture. It will be up here, or I think it's approximately here, the outer mountain. The satellite picture looks like this, and this is the outer mountain in the top. So you should be able to get in from this entrance.
And it's 1:30?
No, it's 1 o'clock.
1 o'clock.
So there's really not too much time. So if you do want to eat beforehand, that might make it slightly tight. What you could alternatively do, you might eat over there somewhere. And
There's some fast food there close to it.
The restaurant is just below the.
this one you mean, right? Yeah, that's the restaurant over here. Yes, that's right. That's one possibility. And then we have our barbecue here at 3 o'clock. And in the meantime, I'll be rushing. I will be there, but
Yeah, but you're taking your bike, and I'm looking for somebody who will walk.
I really walk there. I know the way.
You know the way? Oh, okay.
so then you're.
Okay, let's go.
So then don't forget the barbecue at 3 then.
So let's